I wanted to just say a couple words about how I got here and who I am a little bit. So I managed to just kind of stumble into one of the best jobs on Earth, and that was in college. My girlfriend had moved out to the East Coast. I went to school at the University of Colorado, and she moved out to the Baltimore area at a place called the Johns Hopkins Applied Physics Lab, and I chased her out there, and but the only day that I could get off of work was a holiday weekend, and the only people that were interviewing for jobs on a holiday weekend were people that had to worry about the alignment of the planets in order to do their job. And so the only people that were there were in the space department, and I managed to get a job interview and was accepted, and I started working on New Horizons my very first day. At the time it was in 2003. And they were just building some prototype hardware for the spacecraft. I hung around Alan's coattails for all the decade plus since now, 14 years of working on New Horizons, and it's every time somebody asks me to do something, I'll say yes, and it just means that I'm accumulating more job titles. So I just used to be a test engineer, and I was an RF lead, and the payload system engineer, and the longer I hang around, it seems like the more there is to do. So I did want to say one funny story that happened to me actually the week of Encounter is I was printing out a bunch of posters as thank yous and trying to get Alan and others to sign them. And so I was at the place where the print shop where they were being printed out, and the lady that was operating it, she said, "Oh, well, what are these for?" And I said, "Oh, it's New Horizons. It's going to be in Pluto at 3 days, and you're going to see it on the news." And she said, "Oh, in 3 days? So you didn't get to go?" No, that's a long, cold, one-way trip. So I'm going to talk a little bit. My talk, I'm going to focus a little bit on the overview of the mission, and specifically Australia's role, which has been probably larger than you would think. And then the main event is going to be Alan's turn. So the New Horizons has 7 instruments on board. It's got a high-resolution camera, LORRI, so all the highest resolution images that you see are from LORRI. It stands for Long Range Reconnaissance Imager. It has a color imager and infrared spectrometer called Ralph, a UV spectrometer called Alice, a solar wind and plasma suite, that's Pepsi and SWAP, and the radio science experiment, which is my baby, so you're going to hear more about it than you probably care to. It doesn't make pretty pictures, it just looks like little wiggles on a chart, but those are my wiggles, dang it. So. And there's also a student instrument on board called the Student Dust Counter. So I'm going to show you, this is the entire day of closest approach in fast forward, essentially. So the color imagers are actually it's a scanning image. So you can see as it scans across the target, there's really only a single line of pixels you can think. And in order to build up an image, you have to kind of scan it across. So that's what you're seeing there as scanning across each of the Pluto and its satellites. We kind of approach the Pluto system like a dart to a dartboard. So it's on its side. We're coming at it like a dart. So the closest approach time is almost the same for every single target. So all the satellites in the system, you're the closest to it. So there's a lot to happen all at once. As we cross behind it, we radio back to Earth, and you can see as we fly through the shadows of Pluto and Charon, that's what's going on. And I'm going to be talking specifically about that because that's where Rex is doing its job.
Excuse me, this is very good images. Does someone know about that light?
I can turn that off. Thank you. Is that better? Is that enough? I could also turn the room lights down.
Yeah, very good. Do that.
The room lights off? All right. This is better for me because now you can't see me. That way when I pick my nose, nobody knows. All right. So I mentioned that Australia has a fairly large role in the level 1 science. So the way that the deal with NASA is, what you actually sign up for is the Group 1 or Level 1 science objectives, and we couldn't do it without the REX instrument and without Australia sending those signals to that instrument. It's a radio science instrument, so what happens there is that the ground stations that are over at the Deep Space Network in Canberra transmit a signal up to the spacecraft, and the radio science receiver on board listens, and I'll talk more about that a little later. Some of the other things that involve that same station that's just down the road here, we made the drive a couple days ago, it's about a 3-hour drive, is beacon mode operations. So this is a way for really once a week, we put the spacecraft in hibernation, and then once a week it phones home, and it tells us whether everything is going well or whether or not something happened that we need to actually do something about. So those are called beacons. A green beacon is everything's A-OK, and a red beacon is the spacecraft raising its hand saying, hey, can somebody help? That doesn't happen very often. It happened 3-4 times that I can remember over the course of that 9 years. So it doesn't happen very often, but it's not a fun phone call. Another mode is regenerative ranging. So the way that you actually tell where the spacecraft is, you can't see it obviously when it's that far away. So what you do is you transmit these ranging signals up to the spacecraft, and it's a little like a ping from a submarine. So you send these ranging signals up, and the spacecraft just loops it around and sends it back to Earth. Then it can compare the phase of the signal that it sent and the signal that it received, and the speed of light, and you can figure out exactly how far away the spacecraft is. The problem is that Pluto is 30 times further away than the Earth is to the Sun. So that's a really long way, and it has to go not only all the way up, but all the way back. And there's a lot of noise and very little signal when you do that. So we pioneered a way to do this where you actually lock onto that signal on the spacecraft and then regenerate that signal fresh at the spacecraft and then send it back. So it cuts out half the noise that you could get in the system that way. And another thing that the Deep Space Network here in Canberra did for us is called polarization combining. We have 2 transmitters on board the spacecraft, and each transmits on a different polarization. And then what these huge 70-meter antennas can do is they can actually receive both those signals and then phase them up and constructively add the 2 signals together to get twice the power. So these are all things that were done just down the road here. So I got to actually go see a 70-meter antenna for the first time this week, and they are something to behold. Let me tell you, it's the size of a stadium as an antenna. Not only that, but they transmit up 20 kilowatts. So it's a 20 kilowatt signal. 70 dB of gain is 10 million times. So it's 10 million times more gain than your radio antenna that sticks up at the top of your car. So that's a whole lot of power. It seems like that would be more than enough. It also receives that much. It receives 10 million times more than you'd be able to pick up with your car antenna. Sounds like a lot. But when you're that far away, our encounter was in 2015, and we were using data rates from 1985. So just because of the distance, it's really hard to get high rates. So you can see those arrows pointing on there. Our transmitted commands go up at 2,000 bits per second. And the data that we're getting down typically when we were at Pluto is 1,000 bits per second. At our next target, it'll be typically 500 bits per second. And I'm sure that there are probably some people in the room that can text faster than that. So why the station is so important to us, this is just a graphic that shows the 3 deep space networks. There's one in Madrid, one in California at Goldstone, and then one down the road here at Canberra. And it doesn't take anybody to be able to tell that this Canberra station stands way out for us. New Horizons is over the southern sky. So where the northern latitude stations, just see New Horizons skirting over the horizon, for the Canberra station, it comes way overhead, and you get much longer passes. So we have about 11 hours of a view period instead of 8 hours that we have on the other stations. That makes a big difference. The other thing is that you can imagine there's a whole lot less atmosphere to transmit through if you're transmitting straight up. You know, you're just going through the minimum amount. If it's like you can imagine the sun coming through at a sunset. The reason it turns all red is because it's transmitting through a whole lot of the atmosphere between you and it, as opposed to when it's right overhead and you get really bright light. It's not much different than that. We're not visible light that we're using, but at 8 gigahertz, it's the same effect. That combined with that polarization combining that I talked about earlier is that at the Canberra station, and we can crank that data rate up to 4 times what we can get elsewhere. That might, that sound a lot, so we get a screaming 4,000 bits per second. So maybe we're in the late 80s or early 90s there. This is a little diagram showing the geometry of the encounter. As I said, New Horizons is almost flying at the Pluto system like a dart. I'm about to talk about the occultations, and what that really means is it's a fancy word for watching the light as one thing passes in front of another. So this is done with stellar occultations, which you might have heard about, and we're going to actually, I think there's a press release coming out tomorrow on for our next target. But you can look at a star in the sky, or you've heard about exoplanets. This is how they find exoplanets. You look at a star in the sky, and you just watch the amount of light coming from that star, and it winks out and then comes back, and that's something passing between that star and you. This is pretty much the same thing, but instead of visible light, again, we're using the X-band antennas from Canberra to send the signal up to the spacecraft. And then as the spacecraft flies behind Pluto through its shadow, that light winks out, that X-band signal winks out, and exactly how it does that will tell you some information about the atmosphere. And then it comes back on the other side. So this is the Deep Space Network's now. This is a web page you can go to see what the DSN is ever sending up to whatever missions. This is from that day, from Encounter Day, and you can see we had all 3 Canberra stations. Station 35 hadn't come online yet, so we had every station that Australia would let us use, and everything that we had 4 more stations at Goldstone that were supporting this event. So this is what that occultation looks like. As you can see, as you're coming into the body, you have a nice solid signal, and then it kind of disappears there at the end. So the rate at which that happens and exactly what's happening while it's flying by there tells you a lot about it. But then when it actually disappears entirely, you know that you've actually gone behind the solid body of Pluto. We didn't know how big Pluto was precisely when we went there. So this is how we actually can get a precise measurement. We cut a cord right behind it where that signal is totally gone. And that tells you exactly how large the planet is. We also didn't know really where Pluto was all that well, which is why the ranging and optical navigation that we do is so important. Our closest approach timeline had to deal with about 3 minutes of slop, because we went to within 3 minutes of flight time. We didn't really know where Pluto was going to be. That might not sound like a lot, but 3 minutes at 14 kilometers per second is actually quite a bit. So I told you I was going to tell you more about Rex, and these are my squiggles that I'm so proud of. So I'm sorry that they don't look very pretty. But I want to point out on the right-hand graph there, these are the profiles that we got during that occultation. And one thing that I find fascinating here is that the atmosphere on the inbound leg and the outbound leg looked very different. So that the red curve and the blue curve were very different. And we now know that Pluto, everybody's seen the pictures now, that it's a very different terrain all across Pluto. It's a very diverse. And the entry occultation was over heart shape, the planitia, where the exit was over more of a rocky territory. So this can tell us a little bit more about exactly what the atmosphere is made of and how it varies across the planet. We also get a surface pressure from this. So the surface pressure was very low at the time that we got there, and I think Alan will talk a little bit more about what we think, how it varies over time on Pluto. But it was about 11 microbars. The Rex instrument is also a good thermometer. So it can, based on how much noise is coming off of Pluto, it can tell what the temperature is. Something that's hotter produces more noise. So if you point an antenna at the sun, you get a bunch of noise. But Pluto is about 40 degrees above absolute zero. So I wasn't going to leave my talk without showing you anything pretty. So here's your pretty. And that's really it for me. I'm going to hand it off to the main event now, which is Alan's turn.
Well, hi, everybody. When I was a little kid, the first missions were taking place to explore the planets, and I wanted to grow up and be a part of that. And I was very fortunate after I got a technical education to actually be able to live my dream and be a part of the exploration of our solar system. I've been involved in 29 different space mission teams over time, from suborbital missions to space shuttle missions to interplanetary missions, to the terrestrial planets like Mars and Venus, to comets and asteroids, to Jupiter. But of all those missions, of the 29 that I've been involved in, I've led about half, 14 of them, but New Horizons is hands down my favorite. It really is a dream come true to get to lead a mission to explore the farthest worlds that humans have ever reached out to. And humans are explorers. So it's my opportunity tonight to tell you about New Horizons as a project, soup to nuts, how we did it, why we did it, and what we found. I'm going to start with a little video. This was a video. It's actually called New Horizons. It only runs a couple of minutes. It was made in early 2015, and it summarizes the exploration of the planets up to just before the exploration of Pluto. And it should start right now.
It has been over 3,000 days since we...
Sorry. It doesn't say anything to me. Where's that?
It has been over 3,000 days since we left Earth. We're now since we left Earth.
Thank you.
We're now almost 5 billion kilometers away from home. Out here, where the sun is distant and faint, is a place no one has ever seen before. Pluto and its system of moons, the farthest worlds ever to be explored by humankind. Since the beginning of history, the points of light in the sky have captivated us, particularly those special ones who mysteriously seem to wander. We call them planets. And upon learning that our planet is only one of many in our solar system, how could merely observing these points of light from home ever have been enough? Half a century ago, we began the exploration of all the planets, making ever more distant journeys. Each new world revealed its own startling complexity, character, and unimagined beauty. reaching farther again. Our generation is about to complete the historic first era of planetary exploration.
Well, meet Pluto. We actually did it. We conducted the first exploration of the Pluto system in the summer of 2015. And here behind me you see a true color image of this small planet that orbits on the ragged edge of our solar system. It turned out to be a much more complex world than anybody expected, much more active world. I'll tell you a lot more about that a little bit later, but I want to start at the beginning with this man. His name is Clyde Tombaugh. At the age of 24, he discovered Pluto working at Lowell Observatory in 1930. The discovery was hard enough. It took 25 years to accomplish. But even harder for the technology of the 20th century was to actually learn things about this faraway and very faint target. In fact, for the technology of the 20th century, it was almost impossible to learn about Pluto. Across all those decades of the 30s and the 40s, 50s, 60s, 70s, and 80s, it's a long time, we learned almost nothing. Even by the 1990s, when we had tools like the Hubble Space Telescope, this is the best we could do. You can laugh. It's all right. I'm the PI of the project that took this image. This is the best image of Pluto ever made before New Horizons arrived. Do you see the polar cap at the North Pole? We wrote a lot of papers about that. We overinterpreted those images. That's what we got paid to do. And I think this really illustrates just how hard it is. Here's a world about the size of Australia, 3 billion miles or 5 billion kilometers away. And the thing is, at this resolution, you can't tell very much, can you? The reason we visit the planets is to get enough detail to actually make sense of them and to learn about other worlds so that we can compare them to our own and learn more about the Earth by having other examples. This is the kind of resolution that you need to study a world. It's the minimum, really. From an image like this, we can tell that this planet has continents and oceans and complex weather systems, and we can learn a lot more than that. There you can really see a polar cap. It's at the South Pole. It's called Antarctica. I asked one of my postdocs, Amanda Zangari, to pixelate this image to the same resolution as the Hubble Space Telescope image of Pluto. How's that? What could you learn about the Earth at this resolution? Not so much, huh? That's why we go to the planets. Let me just take that one step further. Who wants to guess what we're looking at? Who said Mars? Good guess, but you're wrong. People fall for it every night. The thing is, it really shows that you need that kind of resolution that you can only get by bringing the cameras and the telescopes up close. And that's why we fly missions to the planet. So you might wonder, there was 26 years of space exploration, 27 years of space exploration from the first planetary mission in 1962 until Voyager finished its job at Neptune in 1989. And across those 27 years, we swept our way as a species, and I'm very proud of the fact that the first mission to every planet was carried out by NASA, and we learned a great deal. But Pluto wasn't on the flight plan for Voyager. And about that time that Voyager was finishing up, some of us who worked on outer solar system problems thought that it would be just dandy if we could go study the Pluto system. And the thing is, we knew it would be expensive. Even a low-cost mission, costing much less than Voyager, would cost about $1 billion. So you got to say to yourself, how do we raise that money? Well, commercial space wasn't quite a thing then. We thought about product placement and different ways that we might attract some funds. There's some pretty good product placement there, don't you think? The longer you look, the more you find. This didn't work out for us, even though it's very funny. What we actually had to do is make a case to our National Academy of Sciences that this should be more highly ranked than anything else. And typically, in every decade, there are about 100 proposals for different good ideas by competent teams, and NASA can only afford to fly a handful. So you have to really rise to the top. It has to be very important in order to get funded. And we had lots of reasons to want to fund a mission to Pluto. It's a complex surface composition. That upper graph that you see behind me shows our infrared reflectance spectrum revealing the presence of various molecules on the surface that are frosts. It's molecular nitrogen, there's methane, that's the CH4, there's carbon monoxide, the CO. And at the relevant temperatures that you can calculate for Pluto's surface, they're all mobile, the same way that water is mobile in the Earth's environment. And in fact, on Mars, there are two volatiles, carbon dioxide and water ice, and it's a very complex place. Pluto promised to be even more complex. In the lower left, you see that graph, which is really the discovery of Pluto's atmosphere by a stellar occultation, like Michael was talking about, in which we watched a star wink out from above Australia in an airborne observatory in 1988 and saw the signature of atmospheric refraction. In the bottom middle, you see that giant impact. That's how Pluto's large moon Charon was formed. And the interesting thing about that is that that's the same way that our moon, Luna, was formed. And we argued that because the Pluto system is the only other place in the solar system where a giant impact formed the primary satellite, that we could learn about the formation of the Earth-Moon by studying Pluto. And finally, we learned that Pluto is a rocky planet. And I know that doesn't quite compute, but you can't judge a book by the cover. And although Pluto is icy on the outside, we know from its density that it's about 70% rock. And for a planet so far from the sun, that was really surprising. And all these facts and others got our mission, our concept to do Pluto missions to the very top, into the A-list. Problem is, there's still too many missions on the A-list to be afforded, so you have to do better than that. And something came along in the 1990s that changed the entire equation. We were studying Pluto missions left and right. You can see a list of these. Studies from 1990 all the way to 2001. Only one, New Horizons, got off the drawing board. All the others never flew because they didn't have enough scientific oomph to get the funding, because we didn't know enough about our solar system to argue powerfully enough that Pluto should not just be on the A-list, but it should be the top grade in the class, the most important thing to do with the funding that's available. How many of you, raise your hands if you ever saw a diagram like this when you were first learning about the solar system? I'll bet a lot of hands will go up, because we all learned at the beginning, back when we were in grade school, that the solar system is arranged this way. 4 little rocky planets on the inside close to the sun, Mercury, Venus, Earth, and Mars in that order. And then there's an asteroid belt. And then 4 very different gargantuan worlds much further out called the gas giants. Jupiter, Saturn, Uranus, and Neptune. And beyond that, there's this little who ordered that misfit called Pluto. It's in a strange orbit. It doesn't fit either pattern. It's not a giant planet. It's not a terrestrial planet. It's just a something else. But if you ever watch CSI on TV or any kind of a detective show, you know that when there's that one drop of blood, that one clue, that's where the whole plot is going to revolve around. It turns out what Tombaugh discovered in 1930 was the harbinger of a whole nother region of our solar system. But the technology wasn't available to find it. Turns out Pluto wasn't a misfit at all. It was the first discovered and the brightest of a whole large population of bodies out beyond Neptune. It's called the Trans-Neptunian region, or more formally, the Kuiper Belt, which Gerard Kuiper, a Dutch-American astronomer, postulated in 1950. But it took until the early 1990s for astronomical detectors, CCD cameras essentially at the back of telescopes, and relatively fast computers for data analysis make it possible for us to actually find the Kuiper Belt. This video, in which we're looking down on a diagram of just the giant planets, there's Neptune rolling along its orbit. All those dots that are appearing are actual discoveries taking place in the 1990s and early 2000s. Pluto's not alone at all. It's part of a vast population. It's the largest member of the population by a lot. But interestingly enough, this third zone of the solar system, the largest structure in the solar system, was not known until the 1990s. When many people in this room, myself included, were taught about the solar system, we thought that the giant planets were the outer planets. It turns out that they're really the middle zone of our solar system. This is the true outer solar system, the Kuiper Belt. And do you see the big dots in there? That's probably the most important part. Along with Pluto, the Kuiper Belt is littered with small planets. And they have funny names like Quaoar and Sedna, Haumea, Ixion, Makemake, Eurus. And they have different colors and different compositions, different numbers of satellites. They are a third class of planet in our solar system. Who knew? There are more dwarf planets out in the Kuiper Belt than all of the terrestrial planets and giant planets combined. Now, who's the misfit now? Well, it turns out when this realization came to our National Academy of Sciences, that there was a third zone to our planetary system, and after 40 years of exploration, we had not sent a single spacecraft there. That by studying Pluto, we could, by extension, begin the exploration of not just this third zone, but the third class of planet in our solar system. Then the priority for Pluto went from a typical A student to the top student in the class. And our National Academy in 2003 ranked this as the #1 priority for funding. NASA conducted a competition. 5 teams formed. New Horizons was one of them. And fortunately for us, we won that competition. We produced a proposal about this thick, like an old New York City phone book, with mechanical designs and electrical designs and trajectory designs and cost plans, management plans, education and public outreach, all of that. So did the other teams, but ours was judged the best. That's the cover of our proposal in the lower right. And once we won it, for 4 years, all we did was work on it. We had to launch in January of 2006 in order to get the last Jupiter gravity assist of the 2000s. Had we missed that launch window, only 3 weeks long, in January of 2006, the spacecraft would have sat on the ground for another 9 years waiting for a Jupiter gravity assist. So the people that worked on New Horizons knew that we were under the gun to produce it on time and on budget. 2,500 Americans worked on this project to build the spacecraft, the instruments, the mission control, to build the launch vehicle, its special purpose third stage, all that. And I just call it the blur. My daughter Sarah was in high school back then, and I was traveling about every week. I would be away at some factory where we were building an instrument or the spacecraft or planning for our launch vehicle, whatever. And she tells stories now about when she was in high school. I don't remember any of them. And the same is true for most of us that worked on the project. It took real dedication and persistence. You know, the Voyager program, 12 years in development. The Galileo mission to orbit Jupiter was 18 years from conception to launch. Cassini, that's orbiting Saturn now and finishing its mission next month. Also 10 years to go from inception to launch. We had 4 years and 2 months, or you can come back in about a decade, try again. So we really had to turn it on. And that team, just an amazing team of people, Michael Vincent, one of them, came through. They did something that had never been done before, built an outer planets mission in 4 years flat. And they did it on cost, for 1/5 of the cost of Voyager. It's a true breakthrough in low-cost outer planet exploration. This is the spacecraft that we built. This is New Horizons. And it's one of my favorite pictures of New Horizons because the thermal blankets, the gold shiny stuff, isn't really finished being installed. And so you can see the aluminum structure of the spacecraft. You can see the big dish antenna that's about 2 meters across on top that we use to communicate with Canberra, DSN, and the other stations in California and in Spain. Off to the right, that black cylinder that looks sort of like a hair curler is not a hair curler. It's a nuclear power generator because we're going so far from the sun that solar arrays don't work. So we have to carry our own power supply. That nuclear power generator is fueled with plutonium. named after the planet Pluto, by the way, when it was discovered in 1939. We bottle it up inside that black cylinder, and its radioactive decay makes that cylinder very hot. It actually generates about 5 kilowatts of heat, and using thermocouples that drive a little voltage difference from the cold side to the hot side of the skin of that device, we generate all the electrical power that runs the spacecraft, about 250 watts at launch. That's about 4 standard American light bulbs. And with that, we run the guidance system, the command and data handling, the communication system, thermal control, star trackers, the gyros, all the scientific instruments. Everything's done on the power of about 4 light bulbs. Inside the spacecraft bus, the box, are all those systems I just talked about, and 2 of each, just like on Noah's Ark. 2 guidance computers, prime and backup, 2 command and data handling computers, 2 sets of transmitters and 2 sets of receivers, so forth and so on. Now, the scientific instruments, we only carry 1 of each, but all the spacecraft systems are twins, so we have a backup. So that if something fails, we can switch to that backup and continue the mission. Fortunately, New Horizons is still operating on its prime systems even 11 years after launch, but we always have a backup plan. Now, I came down here to Australia to give this talk, and the first time I gave it, I found out something very interesting. The man on the far right in that image that's over there, that's Michael. And I never knew that until he told me the other day. It does look like Michael. So that's New Horizons. That's our baby. It weighs about 1,000 pounds at launch, 480 kilos. That includes the fuel that's on board. As I said, it's about the size of a baby grand piano. It's a very small spacecraft. It's actually about the size of this lectern. And we launched it on schedule in January of 2006 on this rocket, an Atlas V. And I have to tell a story. When I was a little kid and I wanted to grow up and be in space exploration, I read every book I could find. I read every NASA pamphlet I could find. I also built model rockets. I spent all my money on those model rockets. I mowed lawns and I washed cars and had all kinds of jobs. I was even a babysitter because I wanted to build more and more rockets. And they kept getting bigger. Can you imagine how much fun it was to pick this rocket out of the catalog? This is the largest, most powerful launch vehicle in the U.S. inventory at that time. And because we wanted to go as fast as possible, we tricked it out. We bought every upgrade that made it more powerful. Was that a kick or what? The most number of solid rocket boosters you could possibly have, the lightest weight nose cone, a special purpose third stage. This launch vehicle is about 70 meters tall. So it's about as tall as a typical downtown skyscraper here in Sydney. But those skyscrapers don't do what an Atlas V can do. Imagine a building taking off so fast that it's pulling 2 Gs within 1 second of liftoff, that it's at 10,000 feet in barely over 10 seconds. Picture a downtown building doing that. That it goes supersonic in half a minute, and that it's in Earth orbit at a speed of 18,000 miles an hour in about half the time that I've been speaking here. I'm going to show you a video of our launch. It's really amazing. How many of you have been to a big rocket launch or a space shuttle launch or anything like that? Can I have a show of hands? Oh, not very many. You guys need to do that. You can see them in Japan. You can see them in China. You can see them in Russia, in the United States, in Kourou, South America, where the European Space Agency launches. You need to go see something like this. I once heard a famous television announcer in the United States named Walter Cronkite say, if you weren't religious before being at a rocket launch, you will be after. So this is the launch of New Horizons.
No Atlas. This is Atlas Launch Control. My team is 10, 9, 8, 7, 6, 5, 4, 3, 2.
rocket boosters run out of fuel after only about 90 seconds. So you'll see them separate very shortly. And they come off in two waves so that they don't collide with one another. First two, and then three more. Now, if you watch closely, you'll see the fairings on the nose cone come off. There they are. We're already at space altitude, so we don't need the aerodynamic profile of a nose cone anymore. New Horizons went behind that cloud, and no one ever saw it again. As I said, in 8 minutes it was in Earth orbit at a speed of 18,000 miles per hour. We flew halfway around the Earth and over Saudi Arabia, where we'd calculated was the point where we should reignite the engines. The second stage ignited, burned to depletion, spun up the third stage for stability. We ignited that solid rocket motor. It burned for 82 seconds. By the end of that burn, our spacecraft was pulling 14 Gs, and it became the fastest spacecraft ever launched. We were off on a journey across the solar system, over 3 billion miles. It took 9 years to do it, but that's not because we were dawdling. Let me give you a metric. When I was a little boy, Apollo astronauts would launch to the moon at 25,000 miles an hour, and it took 3 days to get there. New Horizons reached the orbit of the moon in 9 hours. Wow. The previous spacecraft to reach Jupiter took 6.5 years. We did it in 13 months. It's 500 million miles away. So our 9.5-year journey took a long time because we went a long way. Our job was to intercept the Pluto System in the summer of 2015. Along the way, we had to go to Jupiter in order to get gravity assist that added about 5,000 miles per hour to our speed, essentially for free. But it was also our opportunity to test everything for the Pluto flyby, because Jupiter was the only thing we passed along the way. So this is where our instruments got tested, the spectrometers, the cameras, the other instruments aboard that Michael was telling you about. These are actual images from New Horizons of Jupiter and its volcanic moon Io. And you can see we made a cover of Science magazine, which is kind of the Rolling Stone for geeks. We conducted 700 different scientific observations. We tested all of our onboard flight software for flybys, from image motion compensation to many other kinds of software, and it all worked perfectly. This was our flight test, this was a scientific flyby, and it was our gravity assist. All three rolled into one in February of 2007. And then we launched off across the great gulf of our solar system, crossing the orbits of Saturn in 2008, Uranus in 2011, Neptune in 2014, and then on to intercept Pluto in 2015. It's a nice little graphic, except it looks like we missed. Promise you we didn't. The actual flyby of the Pluto system, to most people, probably to most of you, looked like something that happened over a few days in July of 2015. But actually it began 6 months before, in January, when we began our approach observations, looking for hazards in the system and looking to home in very precisely. So we were taking images of Pluto against the star fields, shipping them back to Earth, and measuring the parallax against the star fields so that we could compute engine burn solutions to trim our course and go exactly where we wanted to go through the Pluto satellite system. We did that for 6 months on approach. The actual flyby was on Bastille Day 2015, when little New Horizons stormed the gates of Pluto and collected 5,000 times as much data as the first missions to Mars and Venus. Put it in big flash memories, solid-state storage on board the spacecraft. And then Michael's little wimpy RF telecommunications system that communicates at 80s rates, which saved us a lot of money by being less capable than other systems, made New Horizons possible, took 16 months to send all that data back to Earth. So for the rest of 2015 and almost all of 2016, presents were raining down from the Kuiper Belt, data sets, one after the next, several hundred of them, The last one came down in late October of last year. Now we have all that data. And what I'm going to do next is tell you about the Pluto system. We went all these years, 26 years from when we started in 1989 till 2015, to sell the mission, and then to win the project, and then to build the spacecraft and its ground system, to launch it and to fly it across the solar system. This is a little family portrait, if you will, of Pluto, its largest moon, Charon, right there in the upper left, and two of its four smaller moons, Styx and Hydra. I'm going to tell you more about each of these objects, as well as the two smallest moons in the system. So let's start with the little ones. Styx, Styx, Kerberos, and Hydra, the four small moons of the Pluto system that orbit in that order, Styx innermost, Hydra outermost. They'd only been points of light until New Horizons arrived, and now we can see they're big icebergs. We actually fingerprinted them chemically. They're made of water ice. They're very reflective. In fact, they're as reflective as freshly driven snow, and that was a surprise. We expected that after 4 billion years out in the radiation environment they're in and being bombarded constantly by micrometeorite dust, that they would darken. But somehow all four of them stay clean as freshly driven snow. We don't understand that, but that's great to have a new mystery. The other thing is, it looks like at least two of them, and maybe more, are actually the agglomeration of smaller moons. That is, Pluto used to have more moons, but they've gotten together by accretion into this final configuration. And we found something else. All four are tumbling much faster than their orbital speeds. Look at the one on the outside. Hydra rotates on its axis almost 100 times for every single orbit of Pluto it makes, which takes about a month. This is very unlike the small satellites of the giant planets that typically face their primary, like the Earth's moon faces us and we only see one face of it, because it's been tidally damped. But something is exciting the rotation states of Pluto's moons. We didn't expect this. In fact, the paper came out in Nature just a few weeks before the flyby, predicting the rotational and obliquity states of these satellites, and it was proven completely wrong 2 months later when we did the flyby. I love that. Okay, so much for the small moons. Here's Charon. This is a pretty large object. It's 1,200 kilometers in diameter. It's made of water ice, on the outside at least. It's about half rock and half ice as a bulk composition, but the surface is water ice with outcrops of NH3, that's ammonia. And it has an interesting geology. It looks like a lot of the icy satellites of Saturn and Uranus and Neptune. If you look closely, you see a lot of craters, don't you? That means it's an old surface. You know, in planetary science, we use the number of craters that we see on a surface to age date it. Here's how that works. If it's raining here in Sydney and you run outside the building with a sheet of paper, the longer you leave it out in the rain, the more dots appear. Well, it's raining impactors in the Kuiper Belt, and the more craters you see, the older a surface is. And so here you see a lot of craters. This is an old surface. In fact, we can calculate its age to be about 4 billion years old. It's as old as the planets. That means that Charon hasn't evolved since that point, else it would show a younger age. Its internal engine ran out of energy shortly after it was born. And if you look at the craters carefully, you'll see some have dark halos and some have bright halos. Those are called ejecta blankets. The halos are the stuff that got excavated out of the holes in the ground. And the fact that some are dark and some are bright is telling us that the interior is different in different places. It's made of different materials. Also, if you look closely across the equator, there's a vast canyon system, which geologists have a fancy name for. They call it the ETB, or Extensional Tectonic Belt. It's a fancy way of saying the planet cracked across its equator. How did it crack? Well, when all that water ice froze, it was liquid during accretion, because the heat of accretion liquefied it. And as it slowly cooled, what happens when water ice freezes? It expands, and that creates great stresses. And it created a canyon system larger than any in the solar system except one, which is on Mars. It's the second largest canyon system in the solar system, 1,200 kilometers long, more than 100 kilometers wide, and 20 kilometers deep in some places. And then, weirdest of all about Charon is the polar cap. You've never seen a polar cap like this because no one had ever seen a polar cap like this. They're usually bright and icy. This one's dark and red. What's going on there? Turns out gases are escaping from Pluto's atmosphere all the time. Just a symmetrical flow away from the planet. Charon blocks a little bit of that, and those gases run into Charon, and where it's coldest at the poles, they stick. And then as ultraviolet sunlight shines on those gases, the nitrogen and the methane from Pluto's atmosphere, they create longer chain nitrile and hydrocarbon molecules, which we can recreate in a laboratory, in a vacuum chamber with a cold finger. And with a solar simulator, we can turn them just this exact color. And we can make a spectrum, which we did with New Horizons, of the surface and fingerprint its composition, and what we make in the laboratory looks just the same. So we think we understand what's going on. The reason that Charon has such a different pull from every other place is that only Pluto is losing its atmosphere to space at this prodigious rate, and Charon just happens to be pretty close, and it's picking some of that up, and then after the gases condense on the surface, the sunlight turns them red. Now, if this theory's right, the South Pole should look the same way, but the thing is, the South Pole is down there off the bottom in polar shadow, just like Antarctica, for a few months each winter. Except on Charon, because of the 250-year orbit, the winter lasts for decades. The next time the South Pole is going to come into sunlight so we can check this theory out is in the 2040s. Stay tuned. We'll tell you if we were right. And what happened there? Did we lose the slide? I guess we did. Well, that's all right. We'll go right to this one.
It's probably a video. Let me see if I can start it.
But it's not a video. No. That's all right. Let's go to the main event. Let's take a look at Pluto. This is an image made up of many smaller images that we mosaic together and wrapped on a sphere to give you the view that you would have if you were an astronaut flying by Pluto on New Horizons. Now, we've stretched the colors. If you look in the upper right, you can see Pluto in true color. And you'll notice that on Pluto, there's a green box, the rectangle. And that rectangle is where the close-up is in the main image. And in the next half dozen or so images, there'll always be something in the upper right with the little context box to show you where we're looking. Anyway, what you're seeing here on Pluto is primarily the left side of Pluto's heart, the western lobe of that heart, which is a vast nitrogen glacier, which we've named Sputnik Planitia. Sputnik was the first satellite, and we're naming lots of features on the surface after historic space missions, because we know that for New Horizons to succeed, we had to stand on the shoulders of all those giants, those pioneers of space exploration. Sputnik Planitia is a nitrogen glacier the size of Texas and Oklahoma combined, about 1 million square kilometers. It's the largest glacier in the solar system. And it's surrounded by mountain ranges that tower 4 or 5 kilometers above the plain. We believe that that whole feature was created in a giant impact, which excavated an enormous hole in the ground on Pluto and raised those mountain ranges as shock waves from the impact when an asteroid 50 or 70 or 100 kilometers across struck Pluto billions of years ago. And the hole in the ground then became a cold trap to the gases in its atmosphere, and it filled up over eons with this nitrogen, which is what Pluto's atmosphere is primarily made of. Take a deep breath. Do that. You're breathing nitrogen. The Earth's atmosphere is 78% nitrogen. Pluto's atmosphere is about 90% nitrogen. So you're breathing mostly the stuff that Pluto's atmosphere is made of every time you take a breath. But on Pluto, because it's so much colder, only 40 degrees above absolute zero, the nitrogen can also condense into a snow, and that snow is what's accumulated in that giant glacier. When we take a close-up of the glacier here in the northwest corner against the mountain ranges are made of water ice. We know that from our spectrometers. Water ice is a very strong material. Nitrogen ice is a very weak material. And the glacier, which abuts the mountains, actually flows around those obstacles, and you can see the flow patterns. The geology on Pluto is actually alive today, 4 billion years after its formation. Unlike Charon and most of the outer worlds of our solar system, Pluto's engine is still running, and that was not expected. How that little planet can still be active after all this time is a mystery that has not been solved since the flyby of New Horizons. When we look in the northeast quadrant of the glacier against these mountains, and this is a topographic map where color equals altitude. The brighter colors are higher up. Let's see if I can use the mouse. Can you see the arrow here? So up here in the mountains, the nitrogen ice pools, and then every now and then, and we don't know if it's because there are earthquakes on Pluto or whether we just build up enough nitrogen that it's going to slump under its own weight, it runs down channels like this one, and you can see it pools out into the main glacier. So we're actually seeing a hydrological cycle where nitrogen is flowing down out of the mountains and recharging the glacier, and in other places we see where the nitrogen is subducting back up under the mountains. So very much like we see in Greenland or in Antarctica on the Earth, Pluto is alive on this vast scale, a feature 1 million square kilometers, and it is geologically alive. When we take a close-up on that glacier, you can't find a single crater across the entire 1 million square kilometers, and that means the glacier is young. It's renewing itself all the time. When we put numbers to that, it has to be less than 30 million years old. That's amazing. That's less than 1% of the age of the planet. And when you look at those images, you'll also notice there are a lot of ovoids, sort of like cells in the ice, not biological cells. Geologically, there are different units that are actually the signature of vertical convection. The ice is overturning in each of those cells because there must be a heat source below. And whether it's due to radioactive decay or the freezing of an ocean inside of Pluto that's releasing latent heat, something is causing that glacier to be alive in many different ways. Now, this is one of my favorite pictures, but not my absolutely favorite picture of Pluto. I'll show you my favorite one later in the talk. This picture was made 15 minutes after we made closest approach. And I like it because it shows Pluto's atmosphere as the haze layers, but it also shows how rugged the surface is. Look how rugged it is in some places. This is a very old place on Pluto's surface. Just next to the glacier, you can see in the little green context box. But there are so many craters that they're one on top of the other. When we age date this place, it's the polar opposite of young. It's 4 billion years old. And it's right next to the youngest place on the planet, Sputnik Planitia. So there are these dramatic gradients as you go from place to place on this little world. What we found is that Pluto is as complex and as variegated as Mars and the Earth. In fact, sometimes we call Pluto the other red planet. It's also got mountain ranges, and those mountain ranges have snow caps. You can see them here. These mountains tower about 5 kilometers above the plain, and the snows on their peaks are not water ice, even though it looks like snow caps in the Rockies where I live in Colorado. That's methane, natural gas, which you can make, again, in a vacuum chamber with a cold finger, and it looks like water ice to the human eye. It makes the same kind of bright white snow caps, but it's actually snow caps made of fuel. Fortunately, there's no oxygen in Pluto's atmosphere because the whole place could go up like kablooey if there was. Here's something else that we found on Pluto's surface that we didn't expect. Large ice volcanoes. This one is about the size of Mauna Loa in Hawaii. And we found 6 of these. And it was completely unexpected. We don't know how Pluto generates these. They're very large. They're very tall. And if you look, you can't find many craters on their surfaces because they're also young. So these large volcanic constructs were also created recently. Everywhere we look, we see something different on Pluto. It's just an amazing little world. Here's my favorite feature on the whole surface. It looks like a frozen lake. It's made of nitrogen. It's about 30 kilometers across. From stereo imaging, we can tell it actually sits in a valley, and it has a shoreline all the way around it. The puzzling thing is, though, Michael gave you the surface pressure that Rex measured, 11 microbars. It's way below the triple point. You can't have liquids on Pluto's surface today. How could there be a lake if you can't get to the triple point where the liquids are stable? This is circumstantial evidence, strong circumstantial evidence that Pluto used to have a thicker atmosphere with much greater pressure. We see other evidence that supports that as well. We see tributaries, things that look like river valleys, also on the surface. Apparently, Pluto goes through atmospheric cycles in which the pressure can be low like it is today, or high, higher even than the pressure at Mars. And then there can be liquids from time to time, about every 4 million years, in fact. Well, I'm going to end the Pluto portion of the talk with this video of New Horizons images that are meant to simulate as if you were flying across the surface of Pluto in a supersonic jet fighter. From the North Pole, where we're going to start right here, across heavily snowy, mantled plains with craters. You can look inside of Pluto there and see layers in the holes in the ground, the craters. You see those tracks that we think might be due to dust devils. And then we're going to fly onto Badlands and then large mountain blocks, 10 to 30 kilometers across, that stretch kilometers into Pluto's sky. And then across a shoreline onto the glacier, Sputnik. You can see those ovoid cells, and if you look closely, you can see dune fields, more evidence of a thicker atmosphere in the past. Pluto is one amazing place. It's teaching us a lot about small planets, and it's telling us that the small planets of the Kuiper Belt are apparently as complex as the inner planets of our solar system. Now that we've finished the Pluto flyby and the transmission of all the data, New Horizons is off on another mission. For 5 years, we'll be exploring objects in the Kuiper Belt. So far, we've used our telescope to study about a dozen of them, to look for satellites, to study their surface properties, to determine their shapes in ways that you can't from the Earth, because the Earth is too far away and we're much closer. Things that even the Hubble Space Telescope can't do. Now, in addition to studying a bunch of Kuiper Belt objects in the distance, we're also going to make another flyby, very close, in fact, closer than we flew by Pluto, of a little object called 2014 MU69. That's just a license plate. We'll get a better name for it. We found it with the Hubble, and we're going to intercept it on January 1st, 2019, about 17 months from right now. Now, MU69 for short isn't nearly as big as Pluto. In fact, it's only about the size of a big mountain on Pluto. But it's important scientifically because these are the objects out of which the small planets like Pluto were made. It's a building block of those planets, and New Horizons will study its geology and its composition and its atmosphere if it has one, and we're going to look for satellites and rings around it and study it to death. And you can come along and watch. It'll be on New Year's Eve and New Year's Day 2019. Before I close the talk, I want to talk about what it was like to be there at the flyby. For those of us that worked on this project for 15 years, to see it work by remote control from 3 billion miles away, it was just amazing. This is a candid image, not a posed shot, of a few members of my science team the first time that they saw Pluto up close, after they'd worked on this for most of their careers. And you can see the energy in the room. People were just electrified by that planet. That just been a smudgy image from the Hubble reveal itself to be a real world overnight on the 14th and 15th of July 2015. But it wasn't just our team that was excited. Thousands of people came to our mission control to be there from all around the United States and other countries. If you look in the back of that image where the slides are being projected, you can see some little numbers, 004. We were doing a countdown. That was 4 seconds before the spacecraft made closest approach. And you could feel the energy in the room, but it wasn't just there. At Mission Control in Maryland at the Johns Hopkins Applied Physics Lab, our website received over 2 billion visits in 2 days. It's about a third of the people on the Earth came to our website during those 2 days. We were on the cover of almost 500 newspapers, front page above the fold, on the same day, on every continent of the Earth, including Antarctica. And I know that because I gave a talk in which I said on all 6 continents where people live, and the one guy that's the editor of the paper in Antarctica wrote me an email and attached a PDF of the cover of his newspaper and said, "Us too." Coolest thing, Google gave us the Google Doodle. If you watch Big Bang Theory, they wrote us into the script. I think Raj was supposedly on our science team. And we were on the cover of a lot of magazines, which you see there. It really caught fire, and it showed people really love exploration. It had been 26 years since Voyager had went to a new planet, Neptune. And 40% of the people on Earth were either not born then or they were too young to remember it. So for a whole new generation, we showed them what first-time exploration was about, and they loved it. It was all over the media. And it was an amazing experience for all of us on our team to be able to generate that kind of excitement about science and exploration through what we had done. I'm going to end on this slide. It's my favorite image of Pluto. This is a true color image looking back at Pluto just an hour after the flyby, with sunlight filtering through Pluto's atmosphere. How many of you have seen images made by Apollo astronauts of the Earth rising over the limb of the moon? Yeah, back in the 1960s, that was a transformational image because nothing like that had ever been seen before. In order to get to a place where you could see the Earth, our planet, rise over the limb of the moon, you had to be orbiting the moon. You had to be there. And this is my favorite image because it's taken from the far side of Pluto. In order to get this image, you have to have completed a Pluto flyby, which is what New Horizons did. Thousands of people worked to make this happen over 26 years. They stuck with it, and they pulled it off on a breakneck schedule and a bargain basement budget. And the other thing about this image that is mind-blowing is that everything you know, the Earth, the Moon, and all the other closer planets are blocked by Pluto in this image. Our entire solar system is behind Pluto. It's amazing what human beings can do. We are a curious species of explorers who've developed a technology to go beyond our home world, and I hope in the 21st century to go beyond robot explorers to send other humans to the planets to even do better explorations and eventually to colonize the planets so that we become a multi-planet species. Thank you very much for coming to hear Michael and I tonight. It's been a pleasure.
Yeah, I saw from one of your slides you're funded till 2021, is that right?
That's right.
Kuiper Belt exploration. How long will the systems last? How long could you go, you think, if you were given the funds? How long could you get useful science back from the Kuiper Belt?
Well, I think we can do science even longer than the spacecraft can last. Michael can tell you about how long, as an engineer, we can probably run this thing.
Yeah, so that, it's a radioactive decay, so there's a half-life, right? We launched with 230 watts of power, but right now we're actually under 200. We're about 195. And that's just going to continue to drain off. So really the limitation for the mission is going to be when we can't keep the lights on anymore, essentially. So if we can't have the computer on to record data, we can't have an instrument on, and we can't transmit it back. The transmitter takes about 30 watts of power by itself. All the core systems of the spacecraft take maybe 150 watts. So we think in the late 2030s maybe is probably going to be about that time. Necessity is the mother of invention, and I think that we'll probably find some tricks that we can play to try to squeeze it out as much as we can. But we're looking in the 2030s, maybe 2040.
And by that time, would you have passed completely through the Kuiper Belt?
We will, and in fact, by that time we'll be potentially in interstellar space.
Right.
Who's next?
Well, you keep addressing it as a planet. Like I asked, or maybe not.
Oh, I see you've been listening to astronomers. People who work on black holes and galaxies and who are not
I
expert.
prefer it's called a planet.
Yeah. Yeah. I personally like the Star Trek test. How many people watch Star Trek? Every week they show up somewhere new, they turn on the viewfinder in the bridge, and sitting out there on your couch, whether they're orbiting a planet or a star or a Klingon cruiser right away, don't you? You can tell an asteroid from a planet, you can tell a comet from an asteroid from a planet, right? If Pluto came on the viewfinder, what would you call it? Yep. So do planetary scientists. The real experts. There you go.
To the back? Yeah.
Yeah, you.
Go ahead.
Is there any estimation on how many of these microplanets are in the Kuiper Belt, or are you expecting?
Microplanets? Hey, wait.
That's fighting words.
I said it's the size of Australia, but we don't call Australia a microcontinent. We estimate that there are probably in our solar system about 1,000 Pluto-sized planets, and probably about a dozen more planets the size of Earth or Mars. Farther out, in the dark, too hard to see yet, but later in the 21st century, we'll probably be able to find them all. So it's really a revolution. The solar system was much better at making planets than anybody expected. And the quaint notion that there were only 8 or 9 is just because the 20th century had a limited technology. I like to make the analogy that if you grew up on a desert island where there are only, say a dozen species of plants and animals, you might think that that's all that ever developed on the Earth. And then if you developed a technology to go to other islands and continents, it would blow your mind to see the diversity of life on Earth. And that's what we're discovering in our solar system, is the solar system was really good at making planets. But most of them are very far away and very hard to find. And we're just now on the lip of detecting them all, beginning with the Kuiper Belt. Who's next?
Does New Horizons have the capability to find some of them?
Does New Horizons have the capability to find some of them? It does not. And the reasons are several-fold, but the biggest single limitation is not the fact that our telescopes are small, it's the fact that our data rates are so low that in order to search, you need to send back very large numbers of images, and we just don't have the telecommunications capability to do it. So we search with telescopes back on the Earth and in Earth orbit.
Yeah. Yes.
So did you, when you went past Pluto, you didn't assist? You got extra push when you went past Pluto? Not close enough to get an assist?
We got a little bit of a gravity assist, but we didn't go close. We picked our trajectory through the system not to gain speed, but to make sure that we had good views of all the objects in the system.
But you could use it as you come.
We could have,
Yes.
at the expense of science. It would have added...
If you find another object out there, so to speak, you then use that to assist yourself again.
Well, the smaller the object, the less it can help you. So Pluto's not nearly as good as Jupiter, and MU-69 hardly makes a difference. It's just the size of like Greater Sydney.
So better to get pictures with data.
Right, exactly.
Okay.
Yes, sir.
Yep.
One of the science objectives of the beginning when you were saying you won because you had such a great proposal was that the moon and the planet had collided. The moon had come from a collision on the planet. Did you find some evidence? What evidence did you find to?
Right, so she asked whether we found more evidence to confirm the notion or the hypothesis that the big moon Charon was created in a giant impact. Well, when we and I say we because we, New Horizons, discovered the 4 small satellites, they're all in the same plane as Charon is. Had they been in random different planes, you might have thought that they were captures or something else, but apparently the whole satellite system was formed in this giant impact. We also find that Charon has precisely the density of Pluto's outer layers, as if it was excavated from that, and Pluto's crust is made of water ice, the same stuff as Charon. So we have lots of circumstantial clues that add up to the same answer, thanks to New Horizons.
Is that also, sorry, to follow up question, is that also why the orbits of the satellites are perpendicular to the solar system?
No, that's for a different reason. Yeah, but the fact that they're all in the same plane together is strong evidence that they were all formed through the same mechanism.
Right at the back, that's standing. Yeah, well, sure.
You're talking about the distance that it could go in the Kuiper Belt. It looked like there were a lot on the map earlier. It looks like there are a lot of rocks out there. Are you worried about hitting anything?
Yeah, whenever we have yeah. I'm not worried about hitting anything. So in an artist's conception, it always looks crowded because the dots are much bigger than the real objects. So it looks like there's a haze of objects and we're going to be like in Star Wars dodging around the edges. But it's completely empty out there. I mean, that is why we call it space, because it's empty. The mean spacing between small Kuiper Belt objects is about the spacing from the Earth to the Sun. And the spacing between the small planets that are out there is about the spacing between the Earth and Pluto. It's really empty. And you have to actually aim to actually get near anything.
Yep.
When you were talking earlier on when you approached Pluto, you were scanning and taking images. How do you actually maneuver the spacecraft to actually do that?
To do that?
No, so we have, I'm not sure how much you know about spacecraft. They're generally speaking, you have two ways of maneuvering a spacecraft. You have reaction wheels or you have thrusters. And on New Horizons, we don't use reaction wheels. We just use thrusters entirely. So we have paired sets of thrusters that give you equal thrust, measured very precisely. And it's because it's so tight of a spacecraft, we're able to actually very finely control and be able to be very agile and scan from one to the next.
You run out of thruster fuel before you run out of power?
We probably will run out, or get close to running out of the tanks of propellant before we can run out of power. At that point, like Voyager did, we would end up just basically, for our spacecraft, we have a spin mode, so we would spin up and we would turn into a heliospheric observatory. So we would just turn on our solar wind instruments and our plasma instruments, and the days of taking images of various things would be over once we run out of fuel. And then we just cruise on out until we run out of power.
Yeah, you mentioned that it was 1/5 the cost of the Voyager probes. Can you explain the reasoning behind that? Is it technology progress? Is it that's because that's all you had? Is it?
So there are two answers to that. The first answer is the mother. That was the only way to do the project. NASA said you get this much money, figure it out, and it was 20% as much as Voyager, and a lot of people thought, that's sucker bait. Those New Horizons guys are going to work on this, and they're never going to be able to pull it off. But we thought very hard about how to do it, and we invented some major simplifications. One was the telecom system that I was giving Michael a little bit of trouble about, right? We simplified the telecommunication system and accepted much lower data rates at Pluto in order to save money. And it wasn't really that the radios were less expensive. It was that by having a lower power telecommunication system, we only needed one nuclear power generator. Voyager needed two. Those babies cost almost $100 million apiece. So in one fell swoop, we reasoned that if you can spend 9.5 years getting there, you can stand to spend one more year getting the data back. You don't have to have it all back in a matter of weeks. And as a result, we saved $100 million. Here's another example. We pioneered spacecraft hibernation, in which the spacecraft sleeps a lot of the time, and you don't need as many people to staff a mission control and all the things that go with that, round the clock, 24/7 for 9.5 years. Voyager took 450 people to run it. We did it on 50 people, 1/10 as many, and those are salaries. And when you add them up over 10 years, say 400 salaries, that's a lot of money. Well, those are two of half a dozen different examples of how we saved money. We also built it very fast. By building it fast, you don't have a standing army cost. So all those things added up. It's also true that, to be fair, Voyager had to build two. We only got to build one. And the end result was that we had a much less expensive mission. So now we've shown the way for others to do more exploration on less money.
On those thermo
The generator.
Electric generators. Have they? I've heard that they don't make them anymore, so they've actually run out for deep space science missions.
That's not. No, that's
not
no.
the case.
The old style ones that we used a spare left over from the Galileo and Cassini's. There's only one left because they built so many back then. They've used them except for the one. There's a new generation that, for example, is on the Mars Curiosity rover and the Mars 2020 rover, and they're available to use and build more of. And so we still have that capability. What you're probably remembering is that for a long time, for about a dozen years, the United States quit producing the fuel. And so you could have the devices, but if you can't put any fuel in the tank, it doesn't do you any good. And in fact, even for New Horizons, about half the plutonium that's on board is Russian plutonium that we bought because there wasn't enough American plutonium around. So there are little blue plutonium atoms and red plutonium atoms. But we made it work.
Thanks so much for that. If and when you go back and send a new spacecraft back, what would you like to do next? If you had a wish list of science you'd like to do next, what would it be?
Well, that's a really timely question. Thanks for asking. There are a lot of people thinking about Pluto orbiters now to go back. And with the new generation of large rockets, like the one called SLS, the Space Launch System, we could actually get an orbiter to Pluto, even though it's going to be a heavier vehicle, faster than New Horizons. We can get out there in about 7 years instead of 9.5. We can break into orbit. And then we can make close flybys of all the satellites, so those fuzzy pictures of Nix and Hydra will turn into sharp pictures. We can get much higher resolution images of Pluto. We can stay there for years and watch as the glacier moves. We can bring along much more sophisticated instruments that were too heavy for New Horizons, like radar that can penetrate through the ice and find the depth of the ice, like thermal mappers that can actually see if the volcanoes are active or what the heat sources are that are driving the convection. We can bring mass spectrometers that can learn a lot more about the atmosphere than the spectrometers that we had. So we got a long wish list, and we're working on that. And hopefully some of the younger people in the room could grow up and be a part of that mission.
I imagine when all of these surface features were discovered, people were having a lot of fun naming them. Like for instance, there was Tombaugh Regio and Morgoth Maculae, Cthulhu Regio. I was just wondering, for both of you, if you have favorite names for some of these surface features?
I have a favorite.
Personally, I like Sputnik Planum. I mean, Sputnik was such a pioneering moment in space history, and you know, I think that's where more than I think my second favorite would be Norgay, because I think that it's awfully cool that we named a feature on a planet after a Sherpa explorer that helped get Hillary to Mount Everest. You know, and I think that this.
And the next mountain range over from Norgay is Hillary Montes on Pluto, by the way. So it's the both of them. My favorite is Tombaugh Regio. You know, as we were approaching Pluto, we started to see every time Pluto would rotate, every 6.4 days, this bright beacon shining at us from 100 million miles away. And, you know, Clyde Tombaugh died in the late 1990s when we were working on getting a mission to Pluto. And he actually asked that if a mission ever got mounted and he had died, that somebody would fly his ashes, and we did. We flew them all the way to Pluto. And, you know, he doesn't get enough credit. He was a giant of 20th century astronomy. He discovered the Kuiper Belt 60 years ahead of its time. People looked, really smart people looked all through the 40s and 50s and all those decades. They couldn't do what Tombaugh did in the 30s until the 1990s. And so that's my favorite feature, is giving the biggest, brightest thing on the planet to Clyde Tombaugh. And the greatest honor in that was that his children were in the room when we named it at the flyby.
Right at the back.
You mentioned that you're planning on sending orbiters around. What about dropping a rover?
I don't think we know enough to send a rover, because we don't know enough about things like the bearing strength of the surface to design that. I think we need an orbiter in order to learn enough to send landers.
You said you flew the inorganic remains of a famous investigator. I was impressed by the efforts you took to stop the construction process becoming contaminated with microbiota. They're pretty tenacious. Did you do some sampling and some culturing to see whether you were successful in keeping human bacteria and the like off your machine?
Well, we have to pay attention whenever we fly a NASA mission to the planets to a set of criteria that NASA have to make sure that we don't contaminate the worlds that we're visiting. In the case of New Horizons, because it was only a flyby and not a lander, because we weren't going to touch the place, the primary requirement for us was to be able to prove to NASA that even in certain failure scenarios that we could make sure that we'd never accidentally crash onto Pluto or any of its satellites. And of course we did. We did that. So, and then as to Tombaugh's remains, of course they're cremains, so they're inert at that point, but they're actually inside of a little brazed aluminum cube, which is sealed, and they can't get out.
Yeah, what was it?
Yes, if we're going to have very large-scale exploration in the future, do we need to maybe reserve some of our radioactive material, uranium or whatever? I read somewhere that if we were to have large-scale nuclear power here on Earth, it's only got maybe like 8 years supply or something. Do you think we should reserve material for space exploration rather than nuclear power?
Wow, I never thought about that. That might even be above my pay grade.
So the Earth's moon is moving away from the Earth over time, whereas Mars and Deimos is moving towards Mars. Do we know yet whether, like, the relative motion of Pluto's moons relative to whether they're moving towards it or away?
So that's a really good question. So he pointed out that Earth's moon is moving away from the Earth very slowly. This is something that's been measured, and it's got to do with the tidal interaction between the two. And as they exchange angular momentum, the moon's orbit slows and it moves further out. By contrast, he pointed out that Mars's two small moons are actually moving in, and when they crash onto the surface. The same physics is at work, but because they orbit backwards, it works with the opposite sign. In the case of Charon, Pluto's big moon, it's not moving in or out because all the tidal interaction is stopped. They've reached the complete equilibrium state where the two spins and the orbit period of the satellite are all the same number. So it's exactly frozen, and it's not moving out or in. Who's next?
Yeah, back there.
Thank you. So you were telling us about the surface composition of Pluto. You only mentioned nitrogen, so pretty much all the surface is frozen nitrogen. Have you detected any other chemical elements in the surface?
Yeah, we have. I showed a spectrum with carbon monoxide, frost, and I mentioned methane quite a number of times, which we also see on the surface. And I mentioned that the mountains are made of water ice. So that's 4 different molecules that we've seen on the surface.
Anything like Hydra?
We haven't seen anything that looks like minerals, because everywhere the snows and ices cover whatever rock is down beneath.
Yeah, up there.
Crashing, the force of propulsion, crashing a lander of some sort or a penetrator of some sort onto Pluto.
That would be a good experiment. I don't think it would be as good of an experiment as an orbiter, but this will sort itself out through the same decadal survey process in the 2020s that we had in the early 2000s to figure out the first mission we should fly be a flyby. As much as I'd like to see a lander in my lifetime, I really think the next step is going to be an orbiter, and only an orbiter.
Over there.
In terms of the electrical systems on the spacecraft, and how you were saying that there were a couple of times throughout the mission where you got like a red beacon or like something had gone wrong. What do you do, I guess, like when you get something like that? Like, is it like, oh no, or you already have, I guess...
You change your underwear.
Yeah. So, you want to do it?
Yeah, so we actually have a ton of contingency procedures that we've worked on, hundreds. that look at every scenario. What we would go to the expert of every subsystem, every box, and say what could possibly go wrong, and we make a huge list. And then we rank that based on likelihood and consequence. So if this happened, we would be totally out of luck. If this happened, it's we'd be a little degraded and that type of thing. And then we rank that work product based on okay, we really have to think about this one, this one, this one, and this one, and we're going to put those in autonomous software on the spacecraft. So the spacecraft then has to be able to take care of itself for the most important things that could go wrong. Then you have another pile of stuff that's ground intervention, where we have our own contingency procedures that we have to follow in order to bring things back online. We have hundreds of different things that we can do.
But about a dozen times in the roughly 12 years that we've flown the spacecraft, it has sent us a message saying, I'm in trouble. And then we look at the telemetry coming down and diagnose what the problem is, and then figure out what we need to do, like switch from the prime to the backup, or change some software, or reset a computer, whatever it might be. And now those things take a while, because even at the speed of light, the signals coming from New Horizons currently take 6 hours to get down to Earth. And if you flip a switch, the moment you see some problem, it takes 6 more hours to get up there. In reality, it's much slower than that, because when a problem occurs, it takes us usually about a day to diagnose it. We have to get enough telemetry to the ground, and then we start taking measures to back out of the problem. And it usually takes us 3 or 4 days of round the clock in order to get things back on course.
Yep, over there.
You mentioned that the Hubble telescope was limited in its ability to see some of the features in our solar system, but we've seen some amazing pictures from deep space that Hubble was able to deliver for us. So why is it limited? What's limiting it?
Oh, because those things in deep space are so enormous compared to planets that even though they're much further away, they're easier to resolve.
Also produce light.
Never in the middle.
That's true too.
Are the full moons, are they spinning chaotic?
That's a really good question. Yeah. It looks like that. And we know that because even before we got close and could see their shapes and surface features on them, we could just measure their brightness. And we did that for several months on approach. And that's called a light curve, when you make a plot of the brightness versus time. And those light curves indicate that they are rotating chaotically.
Over here.
So when you were choosing your launch rocket, were you just looking for what's the most powerful rocket? Did it need to be American?
It didn't necessarily need to be American, but it did need to be something that we could get nuclear qualified. And because foreign launch vehicles don't usually want to show off all their technology and intellectual property, it ended up effectively being a Buy American decision, because in my country, you can't take any real chances when you're launching nuclear material that it might go bad on you. And for the American launch vehicles, we could get all the technical specs and the launch histories and much more detail to show that it would be a safe launch.
Yep, up there in the front.
You said something about the tidal and lake structures. We knew that the atmosphere of Pluto was kind of high pressure. And then you said something about it cycling every 4 million years.
Yes.
What evidence do you have of that, other than just it having a higher pressure?
Right. So there's two kinds of evidence. The first is that in the 1990s, the Nemesis discovered that Pluto's pole oscillates with time, just like the Earth's pole, but much more dramatically. And in the 1920s, there was a scientist in Eastern Europe named Milankovitch who actually explained the origin of the Earth's polar shifts and showed that they correlate with ice ages. So when the tilt would be higher, it would get colder, and when the tilt was less, it would be warmer. And those are now called Milankovitch cycles in honor of his work. In the 1970s, Milankovitch cycles were discovered on Mars, and in the 1990s, they were discovered on Pluto. And now, from New Horizons data, we can actually see evidence of those in the dune fields, in the red polar cap of Charon, which indicates an era of higher escape rates in the past from a thicker atmosphere, and things like the frozen lake and the river valleys that we see that can't exist now, but that could exist during these Milankovitch excursions. And the dynamicists who do all the math calculate the periods. It's 3.8 million years. So we're now about halfway between an extreme and a minimum. If you come back in about 1.9 million years, you can check me out.
All right, so last question. Someone correct? Yes, the gentleman in the green shirt.
Yeah, you mentioned you built it in 4 years because you had that window of opportunity, and if you missed that window, you would have to wait another 9 years.
Yeah.
When's the next window of opportunity? Is that something you're conscious of, in case you need to send another one?
So the next window of opportunity was in 2014, 15, and this year. So that's not happening. And basically, you could think of it this way. Pluto is in some direction. Let's just arbitrarily say it's a direction for pedagogical purposes. Let's say it's in the direction of that exit sign over the door in the back. Pluto's moving very slowly because its orbit takes 250 years. We want to go that way. We want Jupiter to be in position. Jupiter goes around every 12 years. Every 12 years, there are 3 years in which Jupiter is roughly in the direction of Pluto, and you can use it. So in the early 2000s, ending in 2006, and then 12 years later, around now, and then 12 more years from now in the 20s, it'll happen again, and so forth and so on. That's how it works.